Welcome back to the Explainer, everyone. Grab a seat. Today we are going to reverse engineer exactly how engineers build memory out of fundamental logic gates. If you've ever wondered how a completely lifeless piece of silicon actually remembers the data you give it, well, you're in the right place. We're going to break down the exact hardware logic that makes all of our digital storage possible.
Okay, let's dive right in by contrasting the two main types of digital circuits. First, we have combinational circuits. These are super straightforward. Their output depends only on the input signal present at that exact moment. Basically, they have zero memory. The signal just pushes through with a slight propagation delay, and that's it. But sequential circuits, that is where the magic happens. They actually feed the output path directly back into the input side. By using past outputs alongside present inputs, the circuit can remember past states. That feedback loop is the absolute foundation of digital memory.
Here's our syllabus for today. We're going to cover adding memory to logic circuits, synchronous versus asynchronous design, flip-flops and data storage, solving race-around conditions, and finally, some real-world applications in consumer electronics.
All right, part 1, adding memory to logic circuits. Let's tackle our first major engineering problem. How do we actually make a simple logic circuit hold on to a bit of data indefinitely? First, we really need to define our core vocabulary so we know exactly what building blocks we're working with today. A latch is just a basic memory cell. It's capable of storing exactly one bit of binary information, and importantly, it does this without a clock. A flip-flop, on the other hand, is essentially just a latch, but upgraded. It includes additional control inputs, typically driven by a master clock, which strictly dictates exactly when the circuit is allowed to change states. Now, what's really fascinating about a fundamental NOR-based SR latch, where S stands for set and R stands for reset, is the physical schematic itself. The normal output, Q, and the inverted output, Q bar, are actually cross-coupled. They physically loop the signal back on itself, plugging the output of one NOR gate directly into the input of the other. This constant physical loop is what creates a persistent state of memory. And the truth table for this latch acts as our ultimate rulebook. It shows exactly how those inputs map to actions. Send a 1 to set, you write a 1 to memory. Send a 1 to reset, you force it back to a 0. If both inputs are 0, it just holds its previous state. That's our reliable no-change memory condition. But if you fire both set and reset simultaneously, you create a forbidden condition. Because our two outputs are supposed to be perfect opposites, firing both creates a logical short circuit that we absolutely must avoid.
Moving on to part 2, synchronous versus asynchronous design. Because now that we have basic memory established, we face an entirely new problem, which is managing chaos when we connect thousands of these circuits together. To build truly functional computers, we have to choose between two design philosophies. On one hand, we have asynchronous circuits, where events cascade one by one unpredictably, totally unclocked. And on the other, we have synchronous circuits, which are kept in perfect, disciplined order by a master timing device. For any reliable, large-scale system, synchronous design is incredibly vital. So how do these synchronous circuits actually work? Well, synchronous design relies entirely on a central heartbeat, a master clock generator. This generator creates periodic clock pulses and acts as a strict timing device for the whole system. By introducing this clock, we completely transform our basic unclocked latches into flip-flops. This means data is only allowed to be stored or changed when the master clock pulse explicitly says so.
Which brings us nicely to part 3, flip-flops and data storage. Let's see how this clock concept builds our next critical component. A perfect example of this is the D, or delay flip-flop. Remember that forbidden 1-1 state in the SR latch we just talked about? The D flip-flop cleverly solves this. It takes a single input D and slaps an inverter directly between the set and reset terminals. Because of that single NOT date, it is physically impossible for S and R to ever receive a 1 at the exact same time. Problem solved. The forbidden state is completely eliminated. But, simply having a clock isn't quite enough. We also have to decide how the circuit listens to it. With level triggering, the flip-flop is enabled to change states the entire time the clock pulse is running high. The problem is, if your input fluctuates during that wide window, your output is going to undergo multiple unwanted changes. Edge triggering fixes this by strictly limiting state changes to the exact microsecond the clock signal makes a transition. It only triggers on that sharp rising positive edge or the falling negative edge. Part 4, solving race-around conditions. Because even with a clock and edge triggering, physical hardware still has physical limitations, and that leads to our next major engineering hurdle. Imagine applying a clock pulse. No, what if the physical propagation delay of the gates themselves is actually shorter than the duration of that clock pulse? Basically, the circuit is just too fast for its own good. The output will literally toggle back and forth between 0 and 1 while the clock is still high, leaving the final stored value completely ambiguous. In engineering, we call this frustrating loop a race around condition. The elegant solution to this timing crisis is the master-slave configuration. Built using NAND gates, it essentially chains two flip-flops together. The first one, the master, catches the input data on the positive rising edge of the clock pulse. But the slave flip-flop is inverted. It completely ignores the master until the negative falling edge of the clock. By having the master safely hand the data to the slave sequentially like that, we completely neutralize the race around glitch. And finally, Part 5, Applications in Consumer Electronics. Let's step out of the theoretical lab for a second and see exactly where these circuits live in the real world around us. Every single time your smartphone stores a photo in its RAM, or your USB drive holds onto a document, you are relying directly on these exact shift and storage registers. When you use a stopwatch, you're utilizing digital counter circuits. And that digital watch on your wrist, it uses frequency dividers built entirely from synchronized flip-flops to count time perfectly. These schematics aren't just theory. They are the literal blueprints of modern consumer electronics. Which brings us to a really fascinating frontier. We've seen how managing propagation delay and memory states is incredibly delicate, even on a macro scale. If complex modern computing is simply millions of these tiny synchronized flip-flops working perfectly in unison, what happens as we continue to shrink these logic gates down to the size of single attos? As we push the absolute physical limits of engineering, we really have to ask how these fundamental rules of memory will hold up in the quantum realm. It's a massive challenge for the next generation of hardware engineers, and definitely something to chew on until our next explainer.